In this lecture, we're going to start, I guess, a series of lectures, maybe 1, 2, or 3, I'm not sure, on the topic of Newman projections. And this will close out module 2. So Newman projections are a way of depicting conformational isomers because they're sort of awkward to draw on a two-dimensional piece of paper. If you think about it, constitutional isomers, that is structures that are isomeric but differ in their connectivity. We just draw different structures, different connection points, that sort of thing. It's harder to do for free rotation, showing how sigma bonds can rotate and that sort of thing. So we are going to depict conformational isomers and give it some attempts. There are some ways that work that we need to focus on and be able to use. So I guess this is depicting conformational isomers. These are also called torsional isomers. I'll mention that, and I don't think I'll use that word too often, but due to torsion created by twisting the twisting a sigma bond, excuse me, that's where that term comes from. But I'm going to try not to use that. I'll stick with conformational isomer. And if you notice, for those of us that like the details, it's conformational isomer, not conformational isomer. Okay, so I did spell that correctly there, but whatever. Let's get back to the chemistry. So let's say we're going to show a classic example of free rotation. And I'm going to draw the molecule ethane, which is one of our fundamental hydrocarbons that has 2 carbon atoms and then 6 hydrogen atoms. We're fully saturated. And what I'm going to do is focus on free rotation over this middle carbon-carbon bond. Free rotation is happening at all of the carbon-hydrogen bonds, but it's not consequential to the structure because a hydrogen is mostly just a sphere. So if you spin, and I think I've got my structure here, if this green ball is a hydrogen, you just spin it, nothing happens to the structure. Whereas if you've got a structure like this and you rotate it, maybe 60 degrees, this is what the structure is going to look like. Let's depict that. So we're going to do, I'm gonna have my spin arrow here to show that we're rotating, a 60-degree rotation over the CC bond, the only bond that would actually lead to a new structure. I get to pick which side I want to rotate. Remember, if we're going to do free rotation, we should have one side be fixed and the other side rotate. So let's fix the left side and we'll rotate the right side. So if I do that, a 60-degree rotation, I'm going to get to a structure that looks like this. My left side tetrahedron hasn't changed. So if I had my wedge and dash pointing down and to the left, they're going to stay down and to the left. But if I rotate, and I should maybe mention which way I'm rotating, it kind of looks like I'm rotating counterclockwise. It turns out it's not going to matter because all of the atoms are the same. But now I get to this structure where I have a wedge and dash pointing up and to the right as opposed to down and to the right. That's how you get to a 60-degree rotation. Okay, so if my experience serves, many of you probably wrote down structures and can't really, maybe you can visualize, and if you can, I'm impressed. But if you can't visualize how I got from here to here in my structure due to the 60-degree rotation, and I was fairly specific, wasn't I, about 60 degrees, you know, if you can't see that right away, that is okay. And that is why we're going to turn to a different way of depicting free rotation. Hopefully you can see that I've spun the molecule such that the structure has now changed. It's not changed on the right side due to its connectivity. The bonds are still the same, but it has changed in structure, and the only way to really piece together how it changed is to assume that it's undergone free rotation over that carbon-carbon bond. Now what I've done here is I've drawn this in not the most useless way, but not the most useful way of depicting a free rotation event. And that is the above structures are called seesaw structures. It's a kind of a weird word. I get it. And in seesaw structures, what you have are you just have 2 tetrahedral centers that are connected. And so if you depict it I don't really know where the name comes from, but it's typically one where you've got two tetrahedral carbons where the wedges and dashes are pointed up and to the left on the left side or down and to the left. They're pointed, they're in opposite directions. So the wedges and dashes are pointing in opposite directions. And the key thing is the bond of interest is drawn parallel to the plane of the bottom of the paper. Bond undergoing free rotation is parallel. I feel like that's 1R, parallel to the bottom of the paper. Additionally, the atoms are drawn as tetrahedron. So each of the atoms is drawn as a tetrahedron. Okay, so it's two tetrahedral centers connected by one straight line that is undergoing free rotation. It's always this bond. That rotates, and it's drawn in the center parallel to the bottom of the piece of paper. It's a straight line. Okay, so you might say, well, aren't all sigma bonds able to undergo free rotation? Yes, but when we're looking at conformational isomers, and we're typically analyzing one bond that's undergoing free rotation. So we need to focus on that one bond. So I've highlighted that bond. I've said always rotates, indicating that's the bond that we're analyzing. Because what we're doing is we're trying to capture one chemical event or isomeric event, free rotation event, whatever, one of many possible events that could occur. We're trying to capture it and analyze it on a two-dimensional piece of paper. There will be limitations. We have to be careful and make sure we know what we want to focus on. So there's a lot of shortcomings in this depiction. When I said 60 degrees, you were probably like, what? That is such a specific number. Why am I picking 60 degrees? You'll see if we change the depiction to Newman projections. Newman projections are less intuitive, at first a bit awkward, but on the grand scheme of things, in the grand scheme of things, much better. It's not hard, it's just awkward at the start. So it's much better to be sure, but it is awkward at first. Okay, here's what we need to recognize when we're looking at conformational isomers. In truth, we don't need to see, I didn't even need to write that phrase. We really don't need to see the carbon atoms. Wait, what? An organic chemistry professor saying this? But it's sort of true. When I hold the molecule this way, which is kind of a seesaw depiction, I've got my middle bond of interest right here. If that's the bond that I'm hoping to analyze. When I hold the molecule in this position and draw it this way in a seesaw structure, I'm really putting a lot of the emphasis on the black carbon atoms because they seem like they're important. They're the tetrahedral centers. It's their bond that's undergoing free rotation. But I don't really care what's happening to these atoms. I can spin either side. And if you look, the relative position of the carbon atoms is not changing. The carbon atoms don't change position during free rotation. I mean, they're rotating, but it's not them that I'm worried about. It's the things that they're attached to. What does change are the substituents. They are the ones that change position. Now, I know I've just got hydrogens floating around in my original example, but you can imagine as we look into more complicated molecules, we'll just replace those hydrogens with different groups or different substituents to make things interesting. So it's really what the green balls are doing that's important, not the black balls. And as a result, I don't need to see the black balls. Okay? And I really don't need to see the bond. As the bond that's rotating, the whole focal point, the focusing bond is right here. That's not changing position. It's the other bonds that are changing positions. Okay, so the substituents are changing positions. That is, these 1, 2, 3, 4, 5, 6 balls are changing positions. So I only need to see the 6 atoms and bonds connected to each carbon. So it's that number 6 that's important here. Okay, carbon, these 2 elements don't matter, and really this bond doesn't matter. So it's the 3 bonds and the 3 elements attached to either one of the carbons or the 6 atoms total. Now what I'm doing is I'm going to spin this around in my hand, and if you look in this depiction, I can't see the bond. I can see the front carbon atom, but I can see all 6 balls along with their bonds. This is actually the depiction that we want to do. So I've set you up, and we're going to draw this on a piece of paper. That's what we're trying to do, because in this depiction, I can see all 3 white balls and their 3 bonds, and then all 3 green balls and their 3 bonds. So, drawing a Newman projection. And Newman was a scientist. I don't know, so it should be capitalized. I should, but I don't know too much about Newman. So this is a front view of the bond to be analyzed. Well, it always starts the same, a Newman projection. It does. It always starts the same. You always start with a dot and a circle. A dot and a circle. Okay, so the dot and the circle is important, and they is super important. And what they actually mean are these are carbon atoms. This dot is my front carbon, and the circle is my back carbon. Wait, what? If I have the front depiction of my actual model, I don't see a dot and a circle. I see a black ball out in front that's overlapping the black ball that's in the back. That's what we're trying to depict. We're just showing that there's a front carbon atom and a back carbon atom that are undergoing free rotation. And these could be any elements, but for us in this class, they'll only be carbon atoms. So we have a front carbon and a back carbon. The back carbon we draw as this big circle, and the front carbon we draw as a little dot. But we assume that they're actually the same sized elements that are coincidentally overlapping each other due to the perspective that I have. Remember, I care about the 6 bonds and the 6 atoms, not the carbon-carbon bond, and not really the front and back carbon atom themselves. So these are truly overlapped, but drawing this way allows us to see both atoms. It's just kind of awkward. We care about that bond between the 2 carbon atoms. That's the thing that's rotating, but that's not what we're focusing on as we analyze the actual conformational isomer event, or the free rotation event. So we have a dot with a circle around it. Now, what I'm going to do is I'm going to pick a particular arrangement. I'm going to go back here. I'm going to go back to my page of notes, and I'm going to try to do the 60-degree rotation. But we start here, and then we do 60-degree rotation. Why am I starting here? If you look at your notes, I start with 2 atoms that are in plane up, then a wedge coming out, a wedge coming out, a dash coming back towards me, a dash coming back towards me. So this should match our notes. Okay, so what I'm going to do is draw a dot with a circle around it. And this is going to be my starting structure, which I should just redraw, shouldn't I? That's the right thing to do, as opposed to hoping that you all can make that connection back as we learn something new. Okay, so what I'm going to designate is I'm going to designate this star. This is my front carbon. And then this square is back carbon. So my star is kind of right here. My square is kind of right here. Because again, we're going from here to here. Okay. So we have a front and a back. It's kind of like, I'm going to do a really fun sketch. I'm going to draw an eye, and I'm going to show the pathway that the eye is looking. So the eye is looking, and it's reaching the starred carbon before it reaches the squared carbon. Okay? Now what we can do is we can draw the atoms that are attached to the starred and the squared carbon. I'm going to hold off on the square for a second. But I've drawn one of the H atoms pointed straight up. Again, if we're looking at this starred carbon, our eye is bumping into the starred carbon first, it's going to see a hydrogen sticking straight up. So hydrogen sticking straight up. And then if we're looking this way, if we're really looking this way, in this direction, we're going to see a hydrogen sticking down into the left. I'm gonna do colors this way. If we're looking this way, we're going to see a hydrogen sticking down into the left and down into the right, or something like this in terms of directionality. So before I add those hydrogens, just see if you can follow. So we're looking down the atom. Don't worry about the green dots. Let's take the green dots out of here. We've got the white dots. This is what we're looking at when we're turning our head to look. We've got a hydrogen sticking straight up, which I've drawn in my Newman projection on the purple. Then we've got something going down into either the left or the right. And again, I have kind of like mirror camera or something, so I don't want to screw that up. But so on my Newman projection, I could draw a hydrogen sticking down to the left and down to the right. I know this is a tetrahedral center, but if you look, it sort of looks like we're at 1/3 circle separation between the two atoms, doesn't it? It looks like we've taken a circle connecting each of the three atoms together, and each of the three atoms is equally distanced apart, and what looks like it's cutting a circle into thirds. And remember, a circle is 360 degrees. Divided by 3 is equal to 120 degrees. So it looks like they're 120 degrees separated. We know that when we actually like twist it and get out our protractors, when everything's in the same plane, it's 109.5. But from a perspective, it looks to be 120. And that's really useful because we can start to think about thirds of circles and maybe even 1/6 of circles. And that's in fact exactly what I've done when I said I wanted to do a 60-degree rotation. So I'm going to do is take my front carbon and do a 60-degree rotation. So if I rotate 120 degrees, I'm going to take this atom and let it displace the atom that was originally 120 degrees. It's going to put something new at top. 120 degrees is 1/3 of a circle. Whenever I do a 120-degree rotation, do you see how, so here's 120 degrees, 1/3 of a circle. You see how I always am left with a hydrogen sticking up and up to the top? What I'm going to do is I'm going to do half of this rotation. Instead of going all the way down to here, I'm going to stop halfway between the two, and now I have a hydrogen pointing downward. So 60 degrees is halfway between 120, it's halfway to 120. So we go from a hydrogen sticking vertically straight up to straight down, to straight up, whoop, straight up, to straight down, to straight up, to straight down. So 60 degrees is a really nice rotation because we turn a vertical group that was sticking up now to a structure where a vertical group is sticking downwards. And if we wanted to, we could redraw our structure, and I provided this to us on the previous page. So there's our seesaw structure or a seesaw depiction, and my eye hasn't moved. It's still looking down the bond this way. And now if you notice, as it looks to that front carbon, there's a hydrogen that's now in plane or parallel to the carbon that's separating, that's actually doing the rotation. So now that hydrogen is sticking straight down, and I can capture that in my Newman projection. Well, if I'm going to capture that in my Newman projection, I should see that I've got a wedge and a dash that are going to form diagonal substituents that appear to be 120 degrees apart. And that's just a little bit of an illusion based on the way that we're looking down this. We know that they're truly 109.5 degrees apart, but it is helpful to kind of, as we're thinking about rotating over fractions of 360 degrees, it starts to get helpful to have that apparent 120 degree separation. Okay, so I've added the hydrogen atoms now. I've added the hydrogen atoms now that match my seesaw structure for the front carbon atom. If you're having trouble seeing this, remember our eye is going to bump into the carbons where it's bumping into this first carbon, which we show as a dot. Instead of having the square and star, I could have had a dot with a circle. So our eye first bumps into the dot, which we show here. We first bump into the dot, and then we bump into the circle. Ooh. You know what? We could go ahead and attach groups to the circle. When we attach groups to the circle, we want to make sure that we don't have the groups go into the dot, okay? Instead, we want to stop at the circle. So we would just draw a line up from the circle. That shows that we've got a bond to that circle or back carbon atom. Okay, so what is at the back carbon atom? Well, if I focus now, I'm going to go back to my model. I'm going to keep the green fixed, and I'm going to rotate these 60 degrees. And that's going to, again, look like this. So instead of going 120 degrees would be a third of a circle turn, we're going to go to a sixth of a circle turn, or go from a front vertical up to a front vertical down. Now, what does that do to our back? Well, our back hasn't changed, but I'm going to go ahead and take away that front dot. I'll leave behind the carbon-carbon bond, sure. I'm going to leave the front dot out. And so this is my back carbon. This is the circle. So we have a group sticking straight up. And I like to focus on the vertical substituents as I'm first drawing my Newman projection. So I have a group sticking straight up and then down and to the left and down and to the right at an angle. Now, if we look at our Newman projection, this looks, you know, not the, I've seen less aesthetically pleasing things. We've got each of these hydrogens separated from each other by a convenient equal distance. And this is an important thing. It looks like we actually have a name for this particular depiction of the molecule. If you look, this hydrogen shown here is equally between the two hydrogens on the back carbon. We call this a staggered conformation. So the groups in the front sort of stagger or straddle or split the groups in the back. And again, the back is our circle carbons. So this is what, sorry, I'm so bad at this. Like, all right, there we go, good enough. So this is what we're looking at. Okay, and so we got there by doing a 60-degree rotation. 60-degree rotations leave us with a front group. This is our original structure now, where both of the vertical substituents are pointing up. You'll notice that there's an issue with this. All of the groups are now overlapping each other. So let's go back to that original structure. I'm going to make it a little bit bigger so we can see. I always start with a dot with a circle around it. Then I already drew my front substituents going straight up, down and to the left, down and to the right. Okay? Now I need to also have a back group that's going straight up, down and to the left, down and to the right. I'm going to have trouble depicting this unless I sort of tilt the structure so that I can see everything, because the goal is to see the 6 bonds and the 6 atoms that are attached. So when the groups overlap, we need to tilt our Newman projection to see everything. And this is called an eclipsed conformation. Hopefully you can see this. And I guess this is with back. Okay. Hopefully you can see where I get the name eclipse, because staggered, everything was like equally split and it was somewhat aesthetically pleasing to draw. But with eclipsed, everything's overlap and it's kind of a little bit annoying to draw, because if you tilt this atom to the right, you have to tilt this atom kind of down and to the left so that everything kind of twists a little bit. It's like we're taking this structure and we're tilting the back just enough so that we can see everything. And if I move this one over here, got to move this one down here. Ugh. This is very difficult for me and I don't know why. Okay, you have to tilt everything so that you can see everything productively. And you maintain kind of 120-degree separation. Okay, so before we end this first kind of look at Newman projection, we've got things to avoid. Number one, if it's on the circle, don't connect it to the dot. Okay, so let's say I had dot, 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 and then for our staggered conformation, I went all the way into the dot, and I would say, too many things attached to the dot. Because if you draw it inside the circle and connect to the dot, you're saying that the atom is bonded to the dot. So that gets kind of I don't know if I don't really have a harsh highlighting here, but I'm going to put a red square around that. That's a big no-no. We got to make sure that we stop at the circle when it's appropriate, and go into the dot when it's appropriate, to show that 3 things are connected to the dot and 3 things are connected to the circle. Conversely, eclipsed structures must be 120 degrees in the back. And so you want to avoid something where, if we've got this situation, and you also want to extend beyond the circle. You don't want to just stop at the circle. That's also bad. Okay, you want to go beyond the circle so that you can clearly tell that an atom exists. Okay, so what am I getting at with this other point though? So if I tilt my eclipse structure over this way and up this way, this is now less than 120 degrees. So it's less than 120 degrees, apparently. I mean, I know it's 109.5, but the way we've got this depicted, we should be able to see 120 degrees for both, for connections to either the dot or the circle atom. Okay, so that's a quick look at Newman projections. In the next few lectures, we're going to look at how to draw Newman projections from a seesaw molecule or a bond line structure.